So we are talking about principal ideal domains and unique factorization domains, irreducible elements, etc. So let's recall a few things. So R will again be a commutative ring with identity 1. First recall that this notion of a unit. An element U of a ring R is called a unit if there exists a V in the ring such that U times V is 1, which means it has an inverse in the ring. And R star used to denote the set of all units in the ring R. So the units in Z are just 1 and minus 1. These are the elements that have inverses that are integers again. The units in Z mod 6 are 1 and 5. The units in Z mod 12 are, I believe, 1, 5, 7, 11. I mean the images of those elements, of course. Let's put up bars on top so that we don't confuse them with the usual integers. The units in polynomial ring in one variable over a field are just the non-zero constants, meaning the non-zero elements of the field, etc. Okay. And then an element, a non-zero, non-unit element A in the ring R is called an irreducible element if you cannot factor it other than just moving around units. So what I'm saying is that when a non-zero non-unit A is called a irreducible element if whenever you write A as a product of two things, U and V, in the ring, then one of them have to be a unit. Okay, so for example, 7 is a irreducible element in Z because you cannot factor it. Well, you can write 7 as minus 1 times minus 7, but that's just one of them is a unit, so this doesn't count as a factorization. Whereas 6 is not an irreducible element in Z, since you can write it as a product of two things, none of them are units in Z. Okay, so that's some basic language that we already knew. What I want to do first is prove this lemma that I have written out here. Let R be a commutative domain, then prime elements of R are irreducible, and if R is a PID, then the converse holds. Irreducible elements must be prime. So primes are always irreducible, and in a PID, the converse also holds. So in a PID, you can just identify prime elements and irreducible elements, and you can just talk about them interchangeably. So remember what prime means in general. Recall, before we start the proof, recall P in R is prime if prime element means this is a prime ideal, means whenever a product of two elements is in there, then either A or B is there. For all A, B in R. Means AB is in the ideal P means what? Means AB is a multiple of P, meaning P divides AB. Then P divides A or P divides B for all A, B in R. For the last one, I suppose I have to assume that non-zero. Otherwise this divisibility is a little dicey. Okay, so given all this background, let's go through try to get through the proof of this lemma. Part A. let P in R be so here also I suppose non-zero, I should say, because by definition irreducible elements have to be non-zero, whereas 0 could be a prime. 0 element is a prime, we saw if and only if R is a domain. So P be a non-zero prime. And I want to show that it's irreducible. How do I show something is irreducible? Well, pretend that this thing is a product of two elements and try to show that one of those elements is a unit. So suppose P is U times V for some UV in R. And I want to show either U is a unit or V is a unit, but not, since P is a prime, then P is UV, so P divides UV. Since P is a prime, P divides U or P divides V. Now if P divides U, then U is PU1, so P is PU1V, so U1V is 1, since R is a unit, R is a domain. So if you're in a domain, you can cancel P from both sides of this equation and you get U1 times V is 1, so V is a unit. Similarly, exactly same argument, if P divides V, then U is a unit. So that's one implication. This is the easy implication. The part B is where there is some meat. So now you're in a PIDR, and let P be an irreducible element in a PIDR. And I want to show that P is a prime element, meaning what? Let's take two things A and B in the ring such that A times B is in the ideal generated by P. And then I have to show that one of the two elements A or B is in that ideal. So let A be in R such that the product A times B is in the ideal P. I'm trying to show that this is a prime ideal, so I have to show that either A or B is in this ideal. So the trick is to consider the ideal generated by P and A. So let consider the ideal. Let's write this sentence. This is the main non-trivial step. Consider the ideal A, P. So the ideal generated by A and P. Now since we are in a PID, this ideal is principal, so it's generated by a single element. Since R is a PID, one has AP equals X, the ideal generated by X for some X in R. It's a principal ideal. Yes. So then P in particular is in this ideal, so P is X times something for some U in R. But now I can use the condition that P is an irreducible element. Yes, since P is a reducible element, here you have written P as a product of two things. One of them have to be a unit. Since P is irreducible, either X is a unit or U is a unit. Now we have a notation for this. Why am I writing so much? Or U is in R star. Let's consider them separately. Case 1, X is in R star, i.e. 1 is equal to xy for some y in R. So 1 is in the ideal generated by X, which is the ideal generated by A and P. After all, that's the definition. So what does that mean? What are the elements of this ideal generated by A and P? They're all things that look like A times something plus P times something. And 1 is one of those guys for some CD in R. So then B is ABC plus PBD. And now you look at this expression. This AB is in the ideal generated by AB is in the ideal generated by P up here, and P is in the ideal generated by P. So this is in the ideal generated by P, this is in the ideal generated by P, so this whole thing is in the ideal generated by P. So B is in the ideal generated by P. And then case 2, so in this case I get B is in the ideal generated by P. Remember, we have to show that either A or B is in this ideal. Case 2, U is a unit. Then X is U inverse P, because U has an inverse now in R. So X is in the ideal generated by P. So the ideal generated by X is a subset of the ideal generated by P. But A, remember, is in there. A is certainly in the ideal generated by A and P, which is X, which is now in the ideal generated by P. So A is in the ideal generated by P. So what's the upshot? If AB is in the ideal generated by P, then either A is or B is. So we have shown if AB is in P, then either A is in P or B is in P. And when I say in P, I mean in the ideal generated by P. So P is a prime. Next, there is a little discussion about GCDs. You might recognize actually this argument as something similar to arguments that you have seen when talking about GCDs. If you are in a PID and if I give you A1, A2, AN in R, which is a PID, then the ideal generated by them has a generator for some X in R. We say that this X is the GCD of A1, A2, AN. Note that this is only defined up to unit. So if you take the ideal generated by 12 and 18 in Z, that's same as the all multiples of 6. So we say that 6 is the GCD, but it's also same as all multiples of minus 6. So you could also call, by this more general definition, there is no way to choose the positive one. So we just relax that. It's only defined up to a unit. So there's a more detailed discussion of GCD in the notes, but I'll move on.